Yo, yo, what's up? Today I want to work on reading clocks in my Rust OS. So right now I have an OS, and it doesn't have any concept of like time in it. And I thought that would be kind of useful. Specifically, the thing that I was bothered by today is if I go to my OS, stream OS, and I did some off-screen stuff, so let's just pull that in. Okay. So right now, let's enter my development environment. Boom, 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 boom. Right now, when I run, oops. Okay, sorry. One more thing to do for environment setup. There we go. Okay, so right now when I run, this like QEMU window opens and immediately closes. And I thought it'd be nice. This is because I implemented this like I/O device, the driver, I should say, where QEMU says, "Hey, here is an I/O device that you can write to, and when you write to me, I'll just like shut down." And that's kind of useful in some ways, maybe not others. Maybe I don't always want to do this, but I do it on panic. And then I get like the output to the console, so like maybe it's fine. But it'd be nice to be able to like prevent this if I wanted to. And so what I thought would be kind of fun is if I do like a sleep 5 here, and then exit, and then maybe say like if a button was pressed, don't close it, or if no button pressed, only then do we shut down the OS. So like by default, it'll just like print some stuff and shut down. But if we want to like inspect stuff in the debugger or something, like we can do that. It also sets up some nice stuff. So if I was to implement like some sort of like sleep function, what this would have to do is I think the way I'd implement this is with some use of like CPU interrupts. So that sets up interrupt handling pretty well, which is going to be required for some other stuff. And then I thought it might be like, long term, this was going to turn into like some sort of like event loop, right? So at long term, I'll say like while true, probably like do stuff, and then like if no stuff to do, sleep, wait for stuff to do. And this is like kind of like the same thing where I would want to be woken up by the interrupt handler, so this is kind of like a good intro to that kind of thing. And then also, maybe I want to do stuff like on a schedule, and so having like a timer hooked up to the interrupt, it seems like just generally useful. So that's what I want to look at today. Since last time, I did quite a bit of off-screen cleanup, so had a bit of fun yesterday. So what did I do? Let's see. We were probably here, and let's just kind of look through what I did. So I shuffled around the allocator a little bit. Why did I do that? Okay. So my main now looks a little bit more clean. Before I had this like, I had a bunch of printing and like some non-clear like static member accesses here. So I've moved some stuff into like just free functions to indicate like, hey, I'm initializing this segment, and the allocator now owns the global allocator inside it, which makes sense. Instead of main owning it and referencing it and trying to call these like allocator functions all over the place, it's just in one block here. I also added some like testing framework. So right now, if we on the last stream we set up the ability to run cargo test, but it was kind of like a pain to write them. So in the here now, I have this like macro to create a test, and this basically instantiates one of these like test cases. So each test case has a name and like a function associated with it that is a like returns a result. And what my runner now does is, before this took in just like a function to run, and the test function inside owned its like printing of state, and I like didn't really like that. I thought this should be like consistent and generic. So now, instead of getting a function here, I get this test case that gives its name and a test to run that returns a result. And so now I can like look at the result and say, well, if you failed, print the failure, otherwise print okay. Easy. But constructing these is a little bit of a pain in the ass. You have to do like, you have to make a function. So like function my test that returns a result. That's the stuff. And then here I have to like do some stuff and return okay. Like this. And then I have to make like a static test case like this, I think. And here, then I have to give it a name where it's like name is test. And the test is my test. Or something, probably like this. And then I have to like say that this is a test case. And all that is just like extra fluff that I didn't want to write. So what I did instead was I added this macro that does all that for me. So it creates the test case and the test and like does some like how do I say this, concatenation of the input with like some extra identifiers. So it says like, it basically makes like the name underscore test and uses that and makes the static called name. And now when I write tests, it's easy to just say like create test, and then I just write the test. Easy peasy, bing bang boom. I also added this like port allocator. So before, our serial device, he just like started reading and writing to this register OX3F8, and like maybe with a bunch of offsets as well. And he was just like writing there, and that was fine, that was working. But what I was worried about is like, well, how do I know in the future if two people are using the same port and clobbering each other? There's no good way to track that. And so I added this like just simple port manager class that says like, hey, all writes have to go through a port that is allocated through me. And then when I return, when you request a port, I'll like check if it's already in use. And if it's not in use, then I won't give it to you. So just like a little extra safety thing there. Which meant that I had to like kind of like rewrite the serial driver to look a little better, but it's fine. It's nothing too crazy there. So yeah, that's where we're at now. Otherwise, it's the same as where we left off. Let's write up a quick to-do list for today. So what are we doing today? We are setting up RTC clocks and CPU interrupts. And what we've done so far is an off-screen recap. And what we want to do next is learn how to read, let's just call it clocks. Learn how to read a clock. And then later we're going to move on to something else, but that's it for now. So let's just kind of boom, boom, put this guy here. Make sure he's always on top. And then maybe make this a little bigger. Cool. So let's get moving. This guy can go here like this, and we can go. We can look up the OSDev wiki on clocks, or maybe it was timers. OSDev wiki timers, timer interrupt sources. Yeah. So this is like the sources of time that I have available to myself through the operating system, and if I understand correctly, these are kind of like in order of like how I would like which one I want to use. And I think when I was looking at this one looked really promising. So this HPET is access speed very fast, 10 megahertz, so like 100 nanosecond frequency or precision, and I can get interrupts from it. So I was looking at this wiki page, and it's basically saying like, hey, we like read this like ACPI 2.0 table that's used detect presence. So then I started looking at like what the hell ACPI is, which looks like a like power management standard, and it has these like descriptor tables, and if I remember correctly, there's like AML code that's written for it, which is maybe a like do I have to like add an interpreter for this? I think I read that somewhere. Anyways, ACPI seems like maybe a bit complicated as like an initial thing to look at. And it says like, hey, if you can't find it, maybe fall back on PIT, which is this level right below, which is basically the same, except it doesn't have as much precision, right? We had 10 megahertz here. We have 590 kilohertz here. So that's like 20 times slower. But I don't imagine that I'm going to be doing anything that's like requires that much. And then also that we have to like use slow ISA-IO ports instead of memory mapped IO. But we're set up to do that. Again, speed isn't our concern here because our OS does nothing right now. We can always upgrade later. And then I was looking at this and I was like, oh, well, we also have RTC, and we're going to have to implement RTC support if we want like non-monotonic time, which maybe we won't, but I would like kind of like to start with the simplest thing, right? If I look at like the RTC and PIT pages, the RTC page is like pretty short and looks pretty simple, and this PIT page looks like a lot more complex, and like I have to like pick like, do I want square wave generator, rate generator? Like I don't want to like learn all of this right now. I think like if I just want to get some time, this is probably like the easiest way to start. And so I thought, let's start with the RTC. So we'll say here, RTC. Let's say the first thing to do is like read from RTC. So that's where I want to start. We'll get moving. And it turns out, after I was like doing some reading here, that okay, so I think how it works is there's like that battery that sits in your motherboard, and that powers this like CMOS that's some memory that's just sitting there basically all the time, powered by this battery. The RTC actually doesn't control memory at all. The RTC just says like, I'm going to increment time based off this rock that I punch with some electricity, right? I'm going to like, you punch the rock, I wiggle at like a predefined frequency, and I'll increment the number that it's in the CMOS. So the RTC and the CMOS are like connected together, I assume. My mental model is we have like IO that goes to CMOS and RTC, and then these guys like talk to each other. So if I want to read the time, I actually read from this guy, not the RTC. But if I want to like set the time, then I program this, I think. Maybe this. Not sure. But if I want to do something like configuration, like set up interrupts, definitely this guy. Definitely. Yeah, so I think I actually have to read the CMOS first. But let's start with setting up the RTC. So why would I do this? If I turn on RTC interrupts, the RTC will periodically generate IRQ8. And all of this is actually about interrupts. So probably by default, it's just on and ticking. But maybe not with a predefined, like not without interrupts, and that's fine for step 1. Step 2 will be to set up interrupts, but step 1 is just get it moving. Or get reading from it, I should say. So it turns out that this is actually the CMOS that I want to look at. So here they say, here you can get current date and time from RTC, where we select the associated CMOS register in the usual way and read from the port from value 0x71. And here are the registers. So let's start by just trying to get the seconds. If we like just read a couple times in a row, we should probably see that like seconds are incrementing. And so then the usual way, no, that's not it. I was trying to click on usual way. Accessing CMOS is extremely simple, but you always take into account how you want to handle NMI. The fuck is NMI? So let's look up NMI on the OS Dev wiki. Non-maskable interrupt. Hardware-driven interrupt, much like the PIC interrupts, but the NMI goes, okay. What does this have to do with reading CMOS? You select a CMOS register by setting the register number to port OX70, since the OX80 bit of port 70 controls... Okay, hold on. Why would reading from the CMOS also control NMI? So you always end up setting that too. What the fuck? Why? Okay, so NMI. So I think that this just means that, like, hey, there are probably interrupts that, yeah, here we go. NMIs occur for RAM errors and unrecoverable hardware problems. So, what are my options? Just, like, fucking ignore them. Be careful about disabling NMI in the PSE for extended periods of time. Okay, sure. So there's, like, interrupts that supposedly we're not supposed to be able to ignore. But we can, but, like, we shouldn't. And for some fucking reason, reading the clock also might change whether or not we're disabling NMI. That's very cool. Okay. Let's... Is there, like... Oh, here. Non-maskable interrupts is in the CMOS section as well. For frugality in the olden days, many functions were merged together on the chips where there was room, in quotes, even if they did not belong together. Okay, so in the same way NMI could disable was put together with the CMOS control and the real-time clock. That's so fucked. So basically they're just like, yeah, we might run out of bits, so we got some here. The clock only uses the bottom 7 bits, so we'll just put the 8th one. We'll just use the 8th one for NMI. It's okay, like, okay. Sure. Yeah, I guess. Okay, so let's... First, I guess we should just see in our current OS what state NMI is in. And then from there, we can decide what we want to do. In fact, probably... Oh yeah, that's probably fine. So let's look at main, and let's get the port. So I think they said it was 0x70. So we'll say port manager request port 0x70. And if this fails, we say failed to get CMOS port. Well, CMOS / NMI. I wouldn't want to forget that those two are the same. And let's just read. Oh, we have to select the register first. Once a register is selected, you can read the value. Oh, but I want to read the value of 0x70. And, okay, yeah. So let's see. This should tell us, hopefully, this should tell us which register is selected by default and what the NMI bit is. So, we'll just print this, I guess. So, CMOS port status, and we'll print this as like hex, maybe, and we'll close that quote. And now, oopsies, now if I cargo run, OS starts through QEMU, and it tells me it's 0xFF. Does that just mean I can't read it? Yeah, it might. So actually, does that mean... Let's try. So let's just... first, we'll just write 0 to it, and then read it back and see what happens. Yeah, so pretty cool. Assuming that this does anything, we can't read it back. So let's see if we can like check NMI bit. So what is this in B for? Okay. Well, we'll call this port 2. And so 0x71. And so let's just do what this. Well, let's read what this says. The NMI is enabled by the memory module when memory parity error occurs. Be careful when disabling NMI blah blah blah. On the XT, the NMI can be masked by setting 7-bit on IO port A0. But this isn't what the hell is AT? Sorry, XT. Oh, I see. XT and AT are different. I guess I'm on AT, maybe. This port shared with the CMOS RAM index register using bit serial, blah, blah, blah. Expects a read for or write to the data port 71 after any port index, right? Or it may go into an undefined state. So we just have to read. That's so dumb. So we'll call this CMOS data reg, and we'll call this CMOS control reg, and probably CMOS NMI control reg is probably, reg is wrong, these should be ports, and CMOS NMI control port, right, B. So let's do what they say and say write 7F for disable, for NMI enable, and then we will read, we'll just read the byte here, and discard. And once we've discarded, let's see if we can, so what I want to see is I want to see a 0x7F here when I read the control port. But I don't. Okay, so there's just 0 indication from which they were. Can I like check which NMI mode we're in? Check if NMI is on OS dev. It would be nice to know, that's all. I just want to know if it's on or off so I don't change it. But it looks like, at least from this very, very brief test, it doesn't work. Let's try reading the clock to see if like working with the CMOS is working as expected. So where do they say? Here we go, getting the time. So here we'll just try to read register 0. So this is, I think they said do 1 shifted left by 8 to enable NMI. Oh, shifted by 7. So we'll pretend it's disabled by now. And we'll OR this with 0. Okay, fine. I won't OR it with 0. And then if I read 0x71, I should see a number in seconds. So it should be between 0 and 60. And this is where I would normally want to sleep and print it again later, but I can't. So maybe I just loop and see what happens. Oh, okay. So I do see this going up once a second-ish. 22, 23. Okay. So that's cool. So that is all that we need to do to read from the clock. It would be nice to know if we should have NMIs. Let's leave them on, I guess. And I guess we'll notice if something shitty starts happening. Let's do that. Okay. So this will go in IO since the RTC is one of the many input outputs. So let's go into source IO RTC, and in IO mod we'll import this. So we'll say pub mod RTC. Here we'll have a driver for it, and I guess we won't put this. This isn't static at all. We can just put this on the stack. So here we can say we're gonna have a constructor for this thing. And what's it gonna do? The constructor is going to create a new RTC. And right now there's nothing in it, so we just go like RTC like this. And then we make sure that this is public so that we can access it from main. And here, let's say that the RTC is IO RTC RTC new, like this, right? And then we're gonna want to like maybe get the time from it. What are our options in here? So this is, yeah, non-monotonically increasing. This isn't just like a number. This is like a system time. So this is like calling clock get time, not like calling clock monotonic. Although I think if I remember correctly, clock monotonic just sometimes maps to this anyways. But anyways, okay. So let's make a function. Read date. Read. Maybe just read. And it returns like a date time. It'd be kind of fun to pull in Rust's chrono library here. It's kind of funny to like use just like a random library for, well, not random, but like have like proper date time. But maybe that doesn't really make sense. Maybe for now I'll just make my own. So we'll just say year. We'll figure out what goes in here later. And let's just say this is unimplemented. Great, I crashed my language server, so I gotta restart my editor. That's really cool. We'll call this unimplemented. Okay. So presumably I'll need these ports to read the time. So these guys have to go in like this, and have to go in here like this, and they need types. So this is a port, not a prot, a port. This is also port, which means that I need to import IO port. This. Okay. And now to get those ports, we need to pass in the port manager. Like this, and which means we also have to import port manager here. Okay, and then we just pass these bad boys in. So like this, copy this down here, shift them over, and remove type defs. There we go. And I guess this could actually fail, so we'll call this an RTC error, or a RTC init error. And we'll put in proper return types here. So we'll say this is okay or failed to get control reg. And here, this is not control reg, but maybe data reg. And instead of reg, we should call it ports, because these are ports. And now we just have to define this like error type. So here we use RTC init error like this. And now we just have to make it. So enum RTC init error. And we'll pull these guys in like this. Boom, 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 boom. And we'll strip out the okay ors, so like this. Okay, and then what we usually want to do here is derive, debug, and error for it. So I'm using this error no std, to like basically automatically derive display and error types for this. I've done it by hand a bunch, and it's a pain in the ass. You basically have to say like, you have to define impl core format display for RTC init error, and this ends up having like a function display or maybe format. Crash language server. Restart. This usually ends up having like a format with like some stuff in it, and what you end up doing is you just like write this like big match statement, and then for each one you just say like you end up like copy pasting these down, and then doing like write string failed to get control port, and you end up doing this for each one, and then you have to do the same thing for like you have to define the error trait. So you say like impl core error for RTC init error, and then you like have some like types, the functions that you have to define here, where you basically do the same thing where you end up like enumerating all of the options and then like basically doing the same behavior for each of them. So this error basically does all that for me. And I like looked over the source. I'm like, yeah, that's like pretty much what I would do. So I'm pretty happy to pull in this dependency. Usually like I'm maybe a little hesitant, but this one, it's you do the manual way a few times. You're like, I don't want to do this anymore. So let's define our error messages here. And I think we're good. Cool. So now we have to read from these. So what are we going to do? We're going to basically try to get, where are all here? Let's see this. First, you should ensure that you won't be affected by an update. See below. We'll get to that later. For now, these are the components of time that we need to read. So let's do this. We delete a word. We go to the end of it. We go comment this as range. And like this. And then all of these should be lowercase. And there's an extra indent here. We want a semicolon here on all of them. And here we want to make these something. And now we just have to like print, we have to like say what these are. So for now, we'll just make them all 0. Like this. Now, what are we actually going to do here? We're going to read the corresponding, we're going to write the port and read back the data port. So we're going to say, hey, control port, I want to read register for seconds. And I'm going to read it back, and then I'm going to assign that. So probably it just makes sense to like abstract that into a function, because I'm going to be doing that over and over again. And so we can put that up here, and we call this function read port, read CMOS register. And we pass in the control port and the data port and the not register number. So this is I guess probably a U8 in this case. And this is going to return a U8. Now, so here we say control port write B, and we do need to pass in the NMI disable. Let's call this a bool. I guess calling it disable is a little confusing. We should call it NMI enable. If, and then we say we have to like create a mask for the NMI bit based off of the NMI enable flag. So let NMI mask equals if NMI enable, this is going to be 0. else it's going to be 1 shifted left by 7, I think it was. Where do they say? NMI disable bit, shifted left by 7, yeah. Okay, and then we say NMI mask or register. And then we read back from the data port. And that's it. So now for seconds, we say read CMOS reg. We pass in the control port. So this needs to have mute self as a parameter. And then here we can say CMOS NMI control port self dot CMOS NMI data port. And we'll just always enable NMI unconditionally for now. And this is register 0, I think. Was it register 0? So yes, this is 0. This is 2, 4, 6, 7. And this is 8. And this is 9. And century here too. And now, this is where we get fun. We can do a little vim macro where we punch all this in. CMOS NMI control port CMOS NMI self dot CMOS NMI data port. And this is already in. Oh no, true. We need to say keep NMI enabled. And now we just do this for all of them. Boom. Boom, boom, boom. Except this is not CMOS NMI data port. This is CMOS NMI data, CMOS data. There we go. And I forgot to make this mute, so we'll just fix that as well. Boom, boom, boom. And let's just delete these comments because we don't need them. Okay. Now, these are all the things we want on the date time. This. And these are all going to be U8s for now. Oopsies. Why didn't that work? Record the macro. Do thing. Oh, because I didn't finish recording the macro. Oops. So we do this. We do this is gonna be U8. There we go. Okay. So now we just do the same thing here, where we put these guys in here, and we vim macro it out again to do this, and then we do like this, and there we go. So we now read the date time and we send it back. It is kind of weird that they're all U8s. Actually, I also don't even know if they have to be U8s. These are all in the ranges that a U8 would work, so that's fine. And let's derive debug so that we can print this. And then in main, I should just be able to say RTC get, what was the function on it? It was just function read. Yeah, so I should just be able to go to main and call read on it. I do need to pass in the port manager here. And then we can probably just do this where we print the RTC read. And, oh, I see. This needs to say failed to read to construct RTC. And he needs to be mutable, and these guys need to not request their ports to the port manager, else this won't work. And here we just need to prevent this from being a problem. Okay. I think that's it. Cargo check. Cargo run. And we get a date time with minutes 60, seconds 66. Those are the wrong numbers. Right? Oh! Does seconds have the NMI? Second, minutes, hours. Oh, no, these are just... That's odd. Why is that happening? So maybe these aren't U8s. Maybe these are like encoded in some way. Because I should never see hours 33 or seconds 89. So seconds here 37, 39, 39, 40. Okay, so that's working as expected. But I did maybe jump from this. So let's maybe what we can do is if I run target QEMU wrapper target kernel here. Okay, so if I just run this once a second, I can see how this changes over time. So while true time sleep 1, they do this, and then done. What's like a bash while? What's the end of a while? I can't remember. Oh, while I forgot the do. So the done is right, but here I need to write do. Okay. So let's just kind of see. Okay, so 24 to 32. What is happening there? 41, 49. Okay, so let's see if there's something special about 42. So let's look at Python 3, and we'll say print, and this will be a hex formatted 42. 2A. Is this binary encoded decimal? Because 42 would be 210, which doesn't work. That's so silly. Is it actually binary coded? So how do I see what these are? Format, yeah, binary coded decimal. Very cool. That's so silly. That's so silly. Oh, wait. There are 4 formats possible. Binary or BCD mode. I want binary mode. I want binary mode. Put me in binary mode. Okay. So I guess somewhere I configure the RTC to be in binary mode. Binary. Enables binary mode if set. So status register B in the CMOS sets the behavior of the RTC. Maybe the CMOS has like a controller on it that's weird to me. I would think that the RTC would be in control of what format it's writing to the CMOS in. But I guess maybe this makes it so that handling it on the output side means that like the internal format can stay the same, and the CMOS knows that it owns RTC data and it pumps it out the way it wants. That's not crazy, I guess. Okay, so status register B enables 24-hour mode, and status register or binary mode. Okay, so 24 hours. Obviously, I want 24 hours. And, yeah, okay, so we'll do 24 hours in binary. So, in our RTC driver, we'll set this up as, in the initialization, we'll just say, here we'll make a new function also. We'll call this write CMOS reg. Which I guess is kind of, we should just copy paste this. This is a better starting point. And we'll call this write CMOS reg. This doesn't return shit. And we also need to return the value. We need to insert the value, right? Okay, so this is the same as this, where we do the same thing. So we can actually split this out into like get NMI mask, NMI enable, and this turns a U8. Like this, and here we just move this code here, and we take off the variable and return it immediately like this. And this needs to be set on a bool. Now I can say, here I can just directly say get NMI mask NMI enable like this. And arguably we should make like a select register that takes in the control port and the data port and NMI enable. And just put this in here because I know that this is like one line, but it is doing something that's like not really trivial, I guess we could say. So here we'll say select reg, and we pass in control port, data port, NMI enable, and reg. Here we don't need the data port actually, so we'll just take that out, this, and we'll copy paste this here, and we'll say data port write b val. Okay. Very cool, very cool. And now, here on initialization, we just say write CMOS reg. Here, this guy, we pass in the control port, the data port, hardcode true. Let's put this here at the top as a static. The idea being that eventually we probably will want this not hard-coded, and this makes it easier. So let's do this, NMI enable, and register is the status register, so status register B, status register B, where are you at? 0xOB, and we want to write this to, I guess we want to read the status register first, so let status reg equal read CMOS reg, and then we want to set binary mode, so status register B bit 1 value 2. I wonder if bits have got to be low to high, so bit, and are they 0 indexed? Well, yeah, do they have bit 0 anywhere? Bit 0, bit 1, 2. I don't know if these are 0 or 1 indexed, which is frustrating. Oh, value equals 2. They just tell me. Right, so it is 0 index. Oops. So if I want 24-hour mode, if set enables binary. So I want 2 and 4. So status reg or equals 2, or 1 shift left 1, and status reg 1, and we'll say this is enables 24-hour mode, and this enables binary format of time of retrieved values. Okay. Now I just write the status reg back like this, and we can make this mutable so we can write to it, and yeah, that's fine. And let's pull this out into a function just so that it looks kind of nicer there. We could say function enable 24, enable read defaults. Sure. And these will be like this. And this is a bool, or no, this is a port, and mute port. This is also a mute port. This is a bool now, and we don't need to take in the register number because we can remember it here. Here we do this, delete some stuff, lowercase this. These are no longer references, so we delete them, we lowercase this, and we're good. Okay, and here we should probably just set this register number as a constant, so status reg b num is a u8, that is this. And then we replace these with status reg b num, like this. There we go. There we go. Oops, like this. There we go. Okay, so now we just call this function down here. So we say enable read defaults, and we pass this in. We pass this in. We pass in NMI enable. And we call it a day. Delete these. So now, hopefully when I read the clock back, let's build it. Hopefully I see times that increment in a sane manner. 39, 40, okay, 41, 42. Okay, we skipped 42, but that's okay because we're not calling, we're a little delayed. But we should see this start to roll around at 60. So we see 52, 54, 55, and give it to me. Okay, cool. So this is now rolling around as expected. Hours is 21, which means that we're in a 24-hour clock. Let's see if we can write to the RTC. It would be cool to like set the date. Oh, here, okay. So I guess I can just write the values to the clock. So I guess if these are writable as well, these aren't read defaults. This is like enable or set data format, call this, instead of enable read defaults. And there we go. And now let's try like writing a time to here. So let's say pub function write. And this will take in a date time. I guess these are two words, date underscore time. And that is of type date time. And I guess we don't have, like, we don't really have any way of, like, flagging if this, like, succeeds or not. I guess arguably you could, like, write the time, read it back, and then see if that failed. Oh, I also just remembered that they said it's very important that I make sure that I'm doing something, that I'm not affected by an update. So let's actually just check this first. When the chip updates the date, time, and date once per second, it increases seconds and checks if it's rolled over. If seconds don't roll over, minutes. Oh, okay. So this can continue through the time and date registers, but we're pretty slow. This means it's possible to read a time and date while update is in progress and get inconsistent values, right? So I get like seconds that have rolled over, but the minutes haven't incremented yet. So my time could go backwards by a minute. That's what I think that's saying. Oh yeah, here they have an example. Oh, I might read 8:59 or 8:60 or 8 or 9. Yeah, okay. So nice. I could have just kept reading one sentence, but instead I just decided to guess. But that's okay. Oh, we've finished reading from RTC. Let's now do a write to RTC. Let's try that. I guess this isn't quite done because we haven't done this update guard. Okay, so blah, 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 while an update clear, and starts reading in time and date. So we just basically need to wait. Oh, so first is to rely on an update interrupt. And the IRQ handler can safely read the date, time, and date registers without worrying about an update at all. The second alternative, because I don't have any interrupts yet, and is just be prepared for them to just make sure that the update in progress flag is clear, then read the time and date registers, then make sure the update flag progress is clear again, and read all the time. That's so funny. Yeah, okay, we can do that. Okay, so how do we do that? There's an update in progress flag, but like, well, oh, bit 7 of status register A. Okay. So we'll split a function. This is called update in progress, and it will return a bool. This. And what does he do? He selects the status register A. So this is status register A is OA. Makes sense. Status register B is OB. Also makes sense. So we select this guy, and then we read him. And we check if where'd it go? Here we go. If status register A bit 7, so 1 7 shifted left by 7. So if we have bit 7 set, is greater than 0, I guess is all we need to do. So, and this isn't or, this is and. We want to say if only that bit is set, return true. And there we go. Mask and 128 will always be higher than 0. Oh, good warning. Also a good warning. Oh, I'm an idiot. So this should not equal 1 7. Oops. So let's abstract that again. So we'll say const in progress bit mask, we'll call it, equals 1 shifted left by 7, and then we can say in progress mask. Wow, I'm glad that that warning hit me, or else I just would have not noticed that. And oops, this is an or again. How did that happen? There we go. So if the data I read and the in progress mask is not equal to the in progress mask, then it's false, which is what I want. So now, in the read, I just have to do, do this in a loop. We assign the return type like this. And we say while update in progress, while there is an update in progress, using this guy and this guy, the data and control ports, and of course NMI enable. We have to set all of these guys to use NMI enable actually. So while our update is in progress, which uses these 3 things, we just continue, we just hot loop, and if update is in progress, so we copy the same things, I don't want to type it all out again, we just continue. And then ret. Then we break down here if we succeeded. Update may have started while we were reading, in which case we need to read again. Start the loop over. Okay. So now we can check if that still works. So we can cargo build, cargo run. Do I infinite loop is like what I'm really worried about. No, but that was painful. Why is this taking so long? Okay. That's not good. So let's print here. Update happened. Oh no. And let's just see how often that happens. This is not in scope, so probably here it's based off the order. Yeah. So these prints need to be defined before module imports, which is kind of weird. And then really these like use functions should be up here. I see. Okay. So it's just the initial update, I guess. RTC. Print line. Waiting. We'll say, what we're waiting. Why are neither of those lines printing? What the heck? Is my print line broken? Hi, Mick. Oh, what the hell? What is happening? What the? Yeah, hi. Hi. Okay. So something about the RTC read that I just added is causing the CPU to just like hot loop. I wonder why. Let's think about this. So let's see if this causes the same problem. Okay. So I'm seeing waiting and then a high mic after. That's very odd. So let's try disabling this exit for a second. Okay. Something's wrong is happening. I wonder if it's, okay. Theory is I've been worried about the terminal writer, like, going over its allowed memory range and just clobbering RAM. So let's disable this and see if the problem still occurs. Okay, compiling. Okay. The behavior is definitely different. I'm still not getting what I want. I wonder if I'm reading the wrong flag. So let's check this again. Okay. We can take a look at this guy. So this is 1, shifted left by 7. Let's double check that this is right. So update in progress. Blah, blah, blah. Update in progress. Bit 7 of status register A. To read the data problem, you have to wait until update in progress is set to clear. This is not the same as checking if the update in progress flag is clear. Oops. It can take an entire of a second. There are 2 alternatives. Okay, so I could have just set this to... Let's try that mechanism. Well, first let's just check. I want to like sanity check this logic. So, we'll say function in progress max in progress set, and we'll take in status reg A. It's a U8, and we'll return a bool. This guy will be like this. And we'll move this logic down to here. Oh, I'll bet you that there's like a fucking bracket error here. Let's see. And then here we'll call in progress set on the data port read B. Okay. So what we can do now is we can write a test to see if that parsing the logic there is as I expect. So we can say create test, and we'll call it test status or test in progress flag, and he will return okay for now just to make sure that this is all hooked up right. Cargo test. He doesn't like that, probably because the main module is not importing these things in the right order, so maybe this has to be like this. So this guy comes up here. Oh, that's annoying. So I want like the print line macro to be available in tests. Do I? Yes, because the testing runner uses print line. But I also want testing to be available in IO. Because I want to test stuff in IO. That's so annoying. Yeah, they won't like this. Well, let's just double check that that is right. So if I go to RTC here and import or use create testing star. Oh, that's so frustrating. Why didn't I think of this? It's okay. So in IO mod, I can just move the print macros into their own module, which is like kind of icky, but that's fine. So we'll just call it source print rs, and we'll move the print line macros that come here into this guy. And in main, we can now do it in this order where we say mod print line print. Now I think everything works. Nice. Okay, so the test in progress flag is now returning true, and we can look at the mod. What was this called? RTC, and we can just say like test true test. I don't have a function for like test true, so let's implement that really quick. So I have these like macros that basically like wrap printing and returning nicely, similar to like how you have like assertion functions in normal Rust, but I don't want to call assertions because they like crash my program and stop other tests from running. So I have these like test macros, and so I can just say like I can add one that's like test true, and this will take in an expression, and if the expression is not true, then we'll return a formatted string that is the file in line, and we'll just say that A is not true. Okay, and so here I should be able to say test true, like this, and then we can start testing this in progress function. So in progress set, we call it. And let's just try like 1 shifted left by 7 as like their default. And did I forget a bracket here? It doesn't like that because I should need to use superstar here. Ooh, okay, so it doesn't like that. So this is just broken. So let's just double check this. Status reg A. Oops, that should be equals. And then let's try something like this. Oh, I only have 1 byte, so we'll do this. I guess I can just write the hex directly. I'm not that stupid. Okay, so I also need a test false as well if we have a test true. So this is not false. And we swap this. Okay, so we test false. So if we want like the top bit 7 to be set, I think that just means I think that means this should be false and this should be true. So this is oh, maybe I am stupid enough that I need to do the bit masking. First of all, maybe 0x34 is no, because 0x3 should have the we'll just look at Python. We'll admit defeat. And we'll look at Python. Print out some hex values. Boom, 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 boom. Okay. Print 0x34 as a binary number. So can I do like something like this? Yeah. So this is 0, 1, 2, 3, 4, 5. So this should in fact be false. Oh, this should be true. Is that why my tests are failing? Yep. Okay. Cargo run. Let's see now. Main does not have an allocator. Why? Oh, because this guy has to be here. Still no dice. So it prints hello, but this read never finishes. Date time cannot be formatted. Oh. I just wasn't printing it. Okay, so now I think this is actually working as expected now. So let's see. Yeah, okay, that's working pretty quick. And now let's do the while loop again. Yeah, okay, that's working fine now. So let's see how often this is getting through. So in this here, we can say print line restarting. Oh, we have to build it, or else we won't see the output. Okay. Yeah, so it looks like the like colliding with the update is unlikely. It would be nice to be able to test that that logic's working correctly, but I'm not really too worried about it right now. Obviously, there's a way to like write it a little bit better so that you can like split out this, but it's fine. It's fine. Okay, let's remove these print lines. And we'll call that almost ready. Okay, so now we want to say, I want to write a date time and see that the value changed. That's how we can be like really confident that we're doing things correctly here. So I probably want to do the same thing where I factor out this code where I loop to make sure that an update isn't in progress while I write. In which case, it kind of makes sense to have like a function that says like write up like update guarded or something. So let's do that. We pull out a function that says like update guarded read op, and here we'll take in a function that we'll want to run. So this is a function like this, and maybe it returns an R, and R comes in here, and there we go. So we take in a function, we run it, and so now we just set this loop stuff here. Like this. Probably just this whole thing. I can copy paste and then delete the insides. Here we go. So we delete this. And we say ret equals f. And there we go. We don't like all these like selfs kicking around. So this guy actually needs to take in the control part and the data port, but then it can't read them by reference. It won't be like a single mutable reference. So this function needs to also take in the ports like this. And then we need to put them into the function by hand. So we say control port like this, and the data port also needs to be in here like this. And this guy needs to pass in the control port and the data port. Okay. So now I think this is like factored out enough that I can now reuse this like scaffolding for both read and write. And this should be F. Interesting. Try adding a return type. Oh, here. Okay. So now we can probably do update guarded op. And we'll pass in these guys. Like this. And then we'll run like a little lambda that does this. Right? Boom, boom. And hopefully this still compiles. Hopefully. Let's see. Consider changing the closure to take and ignore. Oh. We need to swap all of these out from mute self. Sorry, we need to search and replace and mute self cross CMOS NMI control port with control port, and do the same for self CMOS data port with data port, and then take these in. So control port, data port. Nice, 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 nice. So cargo check, cargo run. Nice, okay. And now we can do the same thing here where we just call update guarded op, pass in the control port and data port, like this, and take in the control port and data port. And now we do the same thing, but instead of read CMOS reg, we call write CMOS reg. And so let's see, how do we can probably vim macro this so I don't have to do anything. So we delete the first word, we delete the second word, and this now gets passed in to the function from date time dot because all the parameter names match. Delete these and change this to a write. And does that run cleanly? Oh, it sure does. That's sick. God, I love it when things work. Okay. So now let's read the CMOS in main. So we'll say let date is this, and we'll print the date. And now we'll say date dot hours equals date dot hours minus 1. And we'll write that now. He's mad because those are private fields, so we just go in here and we say, whoop, you're all public now. Here we say the date hours minus equals 1, and then we write that, so we say rtc.write date, like this. And now what we want to see is that the hours decrement by 1 between these two prints, which we do see, which is very cool. Okay, so we're now confident that we can read and write to the RTC. So this is done, and this is done. And now we want to say, how can we like get interrupts out of the RTC? So we'll say, and like do things on a timer. So use RTC as interrupt timer. So let's like checkpoint here. This is a good, this is like a good little test for now. So here we'll add to our demo prints that we can print the time. So current date is this, and current date minus 1 hour is this. I hope that this doesn't fuck up my real RTC. I didn't really consider that at all. I hope that this is like a completely emulated QEMU RTC and my system clock isn't just like hopping around from this. Yeah. Okay. So here we prove that we can allocate some memory, and then here we prove that we can update the date. Cargo run. Yeah, okay. So we say we've got a vector, we've got a map, we have the current date minus 1 hours. Let's say we actually current date modified in CMOS. We'll call it that. And now our little demo says what we're doing. Easy peasy. Cool. Cool. It doesn't look like my date in the bottom right of my computer is changing, which is a big win there. And we'll call this implement RTC support. So read, add RTC driver that reads and writes to the RTC, to the CMOS, well, we should say. Enabling NMI in the process. Unsure what the previous state was. As we implemented, some things need to move around. to move around. So we moved print line and print were split into their own module so they could be imported before testing, which was imported before IO. I think that's it. I'll update that a little more later. Let's run the lint script. It's mad. Let's run cargo format. Cargo clippy. It doesn't like... Oh, I disabled the terminal writer. I don't remember if that was necessary. I think it wasn't. So let's... Well, I guess we'll find out. So I'll mod terminal writer. This needs to come back. Cargo run. That's fine. Nobody's mad there. Cargo clippy. Is there anything else to complain about? No. Does my lint script complain at all? It doesn't like some of the parentheses in the tests that I wrote for the RTC. So here we'll just do that. And double check that the lint script passes again. Cool. Okay. We are chilling. Okay. So what's up next? Interrupt timers. Okay. So I think here let's look at the CPU interrupt stuff. Let's just say enable CPU interrupts at all. Let's see how that goes. So what we got in here. Interrupts are signals from a device, blah, blah, blah. So from what I've read, there's like, okay, there's an interrupt descriptor table. Things go into these like interrupts from the CPU. So I think there's this thing called the PIC. Okay, sorry, refreshing my memory without really saying anything of note. So if I understand correctly, my mental model of this is that there's a CPU, and in the CPU there's like interrupt lines, IRQ. And I'm kind of like glossing over some stuff here because I don't understand it yet. Like the fact that these IRQs might be managed by like something called a PIC that I'm seeing in here. That like actually, maybe it might be that like this goes to the PIC and this has the IRQ like this. But for the purposes of this like mental understanding, I'm just gonna like ignore that for now. So if I understand correctly, this IRQ might also be mapped to the RTC. Like this. And the RTC says, like, when I count down a certain amount of time, my rock wiggles, the line goes up and down because you, like, punched me, and then, like, when you punch me, I vibrate at a very specific frequency. After a certain amount of time, I'm just going to, like, set this pin high. Maybe, right? Like this goes to a 1 or a 0. And I think what happens is then the CPU, he's like executing some code, right? He's got some like code that he's running. We'll pretend that he's like running lines on a piece of paper. And he's like right here. And he goes like, oh shit, the IRQ happened. Gotta go over here now. And so there's like this like separate function of like IRQ handler. So then he's just like, in the middle of this function, he's just like, whoop, time to go over here. And then he comes back and then just continues. That's my understanding. I'm sure that there's a lot that I've missed here. But that's the model we're working with for now. So how do I program this stuff? We make space for an interrupt descriptor table, which I've hand-wavy assuming is like, you tell the CPU, like, hey, here are the addresses of my functions that you jump to when certain interrupts happen. That's what I think, but who knows? Tell the CPU where that space is. Right, so we LIDT, probably load interrupt descriptor table is my guess of what that stands for. LIDT 86. Let's see. Load interrupt descriptor table register. So loads the values of the source operating the global descriptor table or the interrupt descriptor table. IDT, sure. The source operand specifies 6-bit memory location that contains the base address and the limit of the GDT or IDT. If the operand is blah, blah, blah. So it doesn't actually say what it is. Like, what is the format of this thing? I would assume it's like probably just, if I were to implement this naively, I would just say that like I have like a RAM, like memory here is just like 0040 something. Say I load that, and here I would have like one address per IRQ. So this would be like 0, and this would be like 0, 1, 2, 3, 4, 5. And each of these, and if these guys didn't have functions, I would just put like zeros in here and function addresses in here. But I don't actually know. That's just like what I would guess. So maybe there is somewhere that tells me what the IDT is. Tell that CPU where that space is. Okay. Tell the PIC you no longer want to use the BIOS defaults. Sure. Write a couple of ISR handlers. Yep, for both IRQs and exceptions. Sure. Put the addresses of the ISR in the appropriate descriptors in the interrupt descriptor. Here we go. Interrupt descriptor table. Binary data structure. Sure. Long mode counterpart, blah, blah, blah. Interrupt service routines are located 1 per interrupt vector. It is similar to the global descriptor table. IDD entries are called gates. If you can contain interrupt gates, it can contain interrupt gates, task gates, and trap gates. Sure. Before you implement the IDT, make sure you have a working GDT. No! I don't want to implement a GDT. I don't know what that is yet. Okay. So, every time I've like looked at this, I like don't understand what it's for. Recommended to read the GDT tutorial. So, I think I read somewhere that this is just like a place that you can store stuff. Like it's just like RAM, but like maybe RAM that the CPU can use for certain things. So there's like a null descriptor, 8 bytes wide, and pointer 6 byte wide. I suspect that I'm gonna have to do a lot of reading before I have any idea what this is. And unfortunately, reading and talking to stream at the same time results in me not taking in info. So unfortunately, I think this is going to have to be something that I cover on the next stream, because they're saying here that I can't implement the IDT before I have working GDT. I'd done some like pre-reading on interrupts, and I thought that this was something that I could just kind of like bang out here, but it seems like that's not the case. So I'm going to do some reading off screen on like what this like global descriptor table is for and like how it relates to the interrupt table, etc., etc. And I'll get back to that. I'll work on that tomorrow. So, yeah, if you want to see me struggle with that interrupts, timers, and stuff tomorrow, tune back in at maybe like around 2-ish tomorrow, or you can catch up on my YouTube channel, which is linked in the Twitch description. But yeah, today was pretty good. We got this working. It doesn't look too fancy. Oopsies. Sorry, wrong window maybe? Cargo run. Basically all we did is we got this like RTC reading and writing. Pretty sick, pretty happy with it. Thanks for watching. Catch you on the next one. Bye.